Somewhere in the universe, a star is dying right now. Not burning out, not fading gently into the dark the way our sun eventually will. Not ending with dignity or silence or the quiet dimming of something that has run its course. It is being devoured, pulled apart, shredded, stretched into a thin ribbon of superheated gas and matter and consumed, piece by something so massive, so dense, so gravitationally absolute that nothing it has ever reached for has escaped its grip. Not gas, not dust, not light, not stars. And the thing doing the devouring is not hungry in the way living things are hungry. It does not need, it does not want. It simply pulls, and anything that comes too close becomes part of it forever. It is a black hole, but not the kind that sits quietly in the dark, waiting. This one is active, violent, feeding on a scale so extreme that when astronomers first measured it, they could not immediately find words adequate to describe what they were seeing. There are black holes at the centers of most large galaxies, including ours. The Milky Way's central black hole, called Sagittarius A star, has a mass of about 4 million suns. It is largely quiet, dormant, patient. But other galaxies have something different at their hearts, something awake, something eating. And the most extreme of these, the most active, the most voracious, the most terrifyingly productive destroyers of stars in the observable universe are called quasars. And the most powerful quasar ever discovered is consuming stars, whole burning billions of years old stars, at a rate that will make you question the scale of everything you thought you understood. This is its story, and it begins not with destruction. It begins with a dot of light that puzzled astronomers for decades. In the early days of radio astronomy, in the 1950s and 1960s, astronomers began mapping the sky in radio wavelengths rather than visible light, and they found something strange. Scattered across the sky were intense sources of radio emission, pinpoints, tiny, concentrated, extraordinarily bright in radio frequencies. When astronomers turned optical telescopes toward these radio sources, they found what appeared to be stars, faint, distant, unremarkable-looking points of light. But they were not stars. The spectra were wrong. The light coming from them had been shifted so far toward the red end of the spectrum, stretched so dramatically by the expansion of the universe, that these objects had to be unimaginably far away, billions of light-years distant. And yet they were bright enough to detect. Bright enough, in fact, to outshine entire galaxies. A single point of light, outshining a galaxy containing hundreds of billions of stars. The objects were given a name that captured the confusion surrounding them: quasi-stellar radio sources, quasars. The debate about what they were raged for years. Some astronomers thought they were relatively nearby and simply very strange. Others thought the redshift measurements were wrong. Others proposed entirely new physics to explain them. Then, gradually, the picture came into focus. Quasars are not stars. They are not even close to stars. They are the most luminous, most energetic, most violent objects in the observable universe. At the heart of every quasar is a supermassive black hole. Not a stellar mass black hole formed from a single collapsed star. A supermassive black hole containing millions or billions of times the mass of our sun. And it is not sitting quietly. It is surrounded by an accretion disk, a vast swirling storm of gas and dust and stellar debris spiraling inward at enormous speed, heated by friction and compression to temperatures of millions of degrees, glowing so intensely that the light and radiation pouring outward from this disk, from the region just outside the event horizon where matter is still falling inward, outshines every star in the host galaxy combined. Sometimes by a factor of 100, sometimes 1,000, sometimes more. Quasars are black holes in the act of feeding, actively, violently consuming the matter around them and converting it into the most powerful sustained energy output in the known universe. And then came J0529-4351, a quasar so extreme that when astronomers finally measured it properly, using the Very Large Telescope in Chile and data from the Gaia satellite, the numbers came back at a scale that left the scientific community momentarily speechless. Its catalog name is J0529-4351. It does not yet have a poetic name. No mythology attached, no nickname borrowed from ancient constellations, just a string of coordinates pointing to a location in the southern sky roughly 12 billion light-years from Earth. 12 billion light-years. The light we are receiving from this object right now left it when the universe was less than 2 billion years old, when the cosmos was still in its earliest, most turbulent youth, when galaxies were colliding and merging and feeding their central black holes at rates we do not see in the modern universe. And at the center of this ancient, distant object is a black hole with a mass approximately 17 to 19 billion times the mass of our Sun. 17 to 19 billion solar masses. To put that in context, our own galaxy's central black hole, Sagittarius A star, contains 4 million solar masses and is considered a supermassive black hole. J0529-4351's black hole contains 4,000 times more mass than that. But it is not the mass that defines this object. It is the appetite. J0529-4351 has been measured as the most luminous object ever discovered in the observable universe. Its accretion disk, the churning storm of matter spiraling into the black hole, releases energy equivalent to over 500 trillion times the luminosity of our Sun, every single second. 500 trillion suns worth of energy every second, without pause, without rest, for millions of years. And to maintain that output, to keep the accretion disk fed, to keep the fireworks going, J0529-4351 needs fuel. It consumes approximately the equivalent of 1 solar mass every single day, 1 entire sun every day, not compressed into a black hole through stellar collapse over millions of years, actively consumed, pulled from the surrounding accretion disk, heated to incomprehensible temperatures, and converted into raw energy as it crosses the event horizon. If you were somehow present near J0529-4351, at a safe distance, watching, what you would see would defy description. An accretion disk roughly 7 light-years across. 7 light-years. The distance from our Sun to the nearest star is about 4 light-years. This black hole's dinner plate is wider than that distance. Blazing, swirling, a maelstrom of plasma and radiation so intense that the jets of energy it fires perpendicular to the disk, called relativistic jets, travel at close to the speed of light and extend for hundreds of thousands of light-years into the surrounding intergalactic space. Beams of energy longer than entire galaxies, punching through the cosmos like lighthouse beams from the most powerful lighthouse imaginable. This object has been sitting in our sky this entire time. Astronomers photographed it as far back as 1980. It appeared in survey catalogs. It was logged, filed, unremarkable in the vast inventory of sky objects. It was only in 2023 and 2024 that new analysis identified it for what it truly was, the brightest and most voracious object ever found, hiding in plain sight for 40 years.
Let us get closer. Not dangerously close, not close enough to cross the event horizon and be lost forever, close enough to see. Imagine approaching the accretion disk of a quasar like J0529-4351 from a very great distance. From millions of light-years away, it would appear as an extraordinarily bright point of light, brighter than anything else in the sky, brighter almost than anything the eye could process. As you move closer, still at a safe distance, still millions of light-years out, the structure begins to resolve. The accretion disk becomes visible. not as a flat, clean ring like Saturn's rings, as a turbulent, boiling, asymmetric storm, plasma heated to tens of millions of degrees, material moving at significant fractions of the speed of light as it spirals inward, bright arcs and waves and eddies of superheated matter lit from within by the energy of its own destruction. At the inner edge of the disk, closest to the event horizon, the material moves fastest, brightest, most violent. This is where matter makes its final transition from the observable universe into the black hole itself, the last moment of existence for matter that has perhaps traveled millions of light years to arrive here. A star, an entire star with its own history of millions of years, its own planetary system, perhaps its own quiet story, gets too close. The tidal forces of the black hole are not equal across a star's diameter. The side closest to the black hole is pulled more strongly than the far side. This differential, this gravitational gradient, begins to stretch the star, to elongate it. First, it becomes oval, then it stretches into an elongated shape. Then the outer layers begin to peel away, drawn toward the black hole in a long tidal stream. This event has a name. A tidal disruption event. The star does not fall silently. As it is torn apart, the infalling material heats to extreme temperatures. It flares, it blazes. For a brief period, weeks, sometimes months, the destruction of a single star produces a burst of light that can outshine the entire galaxy it occurred in. A star's death scream visible across the universe. And in the accretion disk of J0529-4351, this is not a rare event. It is Tuesday. Something equivalent to this happening every single day. Stars consumed, energy released, jets fired across intergalactic space, all powered by a single point of infinite density at the center of it all. The black hole does not care. It cannot care. It simply is what it is, the most efficient energy converter in the known universe, converting mass into energy with an efficiency that nuclear fusion, the process that powers every star, cannot come close to matching. A black hole's accretion process converts up to 40% of infalling mass directly into energy. Nuclear fusion, by comparison, converts less than 1%. The black hole is not just the most destructive thing in the universe, it is also the most efficient. And in the long, cold future of the cosmos, when the last stars have burned out and the universe has grown dark and cold, black holes will be among the last things remaining. Long after the lights go out, they will persist, patient, dense, slowly evaporating through a process called Hawking radiation, over timescales so vast they make the current age of the universe feel like an instant. The universe begins with a bang, and it ends, in a sense, in the patient, inevitable darkness of the last black holes dimming to nothing. There is a kind of awe that is very close to fear. Most emotions have clear boundaries. Joy is joy, sadness is sadness. They stay in their lanes, but awe does not. Awe lives in the borderland between wonder and terror. It is what you feel when something is so much larger, so much more powerful, so much more extreme than anything your mind was built to process, that the categories break down and you're left with just the feeling. Raw, unnamed, enormous. That is what J0529-4351 produces, a black hole consuming the mass of an entire star every single day, shining with the light of 500 trillion suns, sitting at the center of a galaxy 12 billion light-years away, screaming its existence across the universe in every wavelength of light and radiation we can measure. It is not threatening us. It is not coming for us. It will be gone, consumed into the deep future of a cooling cosmos, long before anything it does could touch us. But it is real, and its reality forces a reckoning. We live on a planet that is, by cosmic standards, extraordinarily peaceful. Our sun is stable and mild and generous. Our solar system is quiet. The nearest major gravitational threat to Earth is billions of light years away. We are sheltered, protected by distance and orbital mechanics and the sheer statistical improbability of anything catastrophic finding us. And yet, we found it. We found the most luminous object in the observable universe. We measured its mass, its luminosity, its rate of consumption. We calculated how many stars it devours per day. We traced the light that left it 12 billion years ago and decoded the story it carries. This is not a small thing. Every era of human history has had its monsters, the things that live beyond the edge of the known world, the darkness past the firelight, the deep water, the far horizon. And every era eventually has found a way to illuminate the monsters, to measure them, to name them, to understand them well enough that the terror does not disappear, but it transforms. It becomes knowledge. And knowledge, even of terrible things, is better than ignorance of them. J0529-4351 is the largest monster we have ever found, the most powerful thing in the observable universe, a black hole that eats stars every day, without pause, without mercy, without end. And we know about it. We measured it. We named it. We sat in observatories and conference rooms and offices with too much coffee and not enough sleep, and we worked out what it was and what it was doing and what it meant. That act, that stubborn, relentless, deeply human act of looking at the darkness and refusing to look away is not small. It is everything. Because in a universe that contains objects like J0529-4351, objects that consume suns the way we consume days, the fact that something small and fragile and brief looked up and understood it is the most extraordinary thing in the story. More extraordinary than the quasar itself. More extraordinary than any black hole, any tidal disruption event, any jet of energy crossing hundreds of thousands of light years. A mind that grasped it. That is the real miracle. That is what makes the darkness worth looking into. Every single time.